Let me introduce RJ. Let me introduce you here, and then we'll let you take it away with your presentation. RJ Nowling's an open source developer and an advocate with Memphis.dev, and he's also a associate professor of computer science at the Milwaukee School of Engineering. Then he earned his PhD in computer science and engineering from the University of Notre Dame. I think I've heard of that school. But, anyway, welcome, RJ. And RJ is going to present tonight on change data capture.
Well, thanks, Ross. I want to thank Ross and Jared and the rest of you for the opportunity to speak with you tonight. So I'm going to be talking about sort of an example application using change data capture and talk through some open source technologies that can be used to architect that and implement that. So I'll spend a little time talking through some slides, but then we'll do a live demo. So if that sounds good to everybody. I was already introduced, so we don't need to really go through that. But I will say that between my PhD and being a professor at MSOE, I was a machine learning engineer in industry for 4 years. So I was actually at Red Hat for 2 years, contributing to Apache projects in the big data space. And then I was at an online advertising company building machine learning models to predict whether you were going to click on an ad to figure out which ad to show you. So that's my background. And so I kind of want to start with, I think maybe most of us, right? I'm assuming this group is familiar with using databases. And the way we implement or work with a SQL database usually, right, is our application establishes a connection to the database. And it will execute a SQL query. And that SQL query creates effectively a temporary table that gets streamed back to the application, right? And so whether we're selecting data to get, query it to get out of the database, or we're inserting data, everything's driven by the application, okay? Now, it's sometimes really useful to have cases where when the records in the database change, other applications can listen for this and receive those update events. Right. So we're going to talk about change data capture, which is a set of technologies that allow us to use this sort of event-driven architecture and to receive messages from the database of, hey, this record was created, this record was updated or deleted, and respond to that. So, oops. And this is maybe a more complex example. We don't want to necessarily go through all of it, but this is an example of a machine learning sort of system where we have a REST service that is ingesting data into a database, a SQL database. And then we'll be talking about using Debezium server to basically capture records as they're written to the database and put them through basically Memphis, which is an event processing system. So you can think of it as like RabbitMQ or Kafka, and then basically process all those events to train machine learning models and then deploy them. So our application is based on this idea that, or we have this small sort of web application or service here that then another service can listen for those change events. If you've ever done GUI programming, this is a lot like the observer pattern, where you have, an observable object and an observer, and the observer listens for notifications. So it's the same idea. And the nice thing about change data capture as a solution is that you don't have to actually change the application itself, right? So it's transparent to the application that these events are being sent. If you compare that to other patterns where you might need to create a separate table, to duplicate the events and use that table as like a queue for events to be processed, you'd have to change your schema, maybe modify your application logic to add additional insert statements or triggers to your database or other mechanisms. So change data capture is transparent to the application, which is nice. Today, the example application we're going to go over is actually really simple. It's just a to-do item. So we're going to have like a single table that has to-do items in it. And each to-do item is going to have a description. It's going to have an ID, a timestamp at which it was created, an optional due date, and then a Boolean value indicating whether the item has been completed or not. And what we're talking about today works with both MongoDB and Postgres. So I'll talk a little bit about both of them. So what our application starts with is we have just a simulator that generates to-do items, and it pushes them into our database. So it inserts them into a collection in MongoDB. And Debezium server is listening to MongoDB for those changes. And when it receives them, it pushes them via REST to our message broker. And our message broker has two stations, which other systems might call topics or subjects. One for the raw CDC events. And this has two listeners. So there's a consumer for just printing to the console for debugging purposes. And then we're actually going to transform those messages so that then we can to kind of clean them up. And we're going to look at a technique that is pretty powerful for preventing bad records or malformed records from getting into our pipeline. And then we'll print those out. And we'll talk kind of about the motivations for that. Are there any questions so far or anything I can help with? Okay. So how does change data capture work? Again, I kind of assume this audience has a hands-on experience with databases. A lot of databases, Postgres, SQL Server, and MongoDB support replication, right? Now, I'm not necessarily talking about distributed databases like Cassandra or CockroachDB. I'm talking about a more traditional database. And in that case, you're going to have a primary or a leader that is going to be able to, it's what the clients are primarily going to connect to, especially if they need to do writes. And then changes within that primary node are replicated to the other nodes. So what ends up happening is if this primary node fails, one of the other nodes can take over as the primary replica. So the data is not distributed across it. Every server has the same exact copy of the data. Well, the way this is implemented in databases is they use something called a write-ahead log. And this is often part of like their support for transactions as well, is they have a log that changes get written to. It's a reliability feature. And what change data capture, the way that this replication works is that basically those log events are replicated to the other instances of the server. With change data capture, we effectively are going to, the change data capture Debezium is going to act like a replica. It's going to receive those changes from the write-ahead log and then basically reformat them and pass them on. So Debezium itself is an open source project. It started at Red Hat, and this has a bunch of connectors for various databases that allow it to basically, like when you point Debezium at your database, it handles a lot of the configuration for you, and then basically will listen for events. Debezium originally was designed as connectors for Kafka. So if you're not familiar with Kafka, it's a event streaming platform. It's a message broker basically, but it's durable, so the events stick around even after you process them, so you can go back and reprocess them. And the idea behind a Kafka connectors is that you have your cluster of Kafka instances running, and the connectors actually run directly on the cluster, so they're like plugins. So the thing is not everybody necessarily wants to run Kafka. I work for a company that is a competitor to Kafka. So Memphis is developing an alternative message broker. And you may have reasons for using one product or another, but I know that for like one of the reasons our customers like our product is that there's a lot less operational overhead. It's a lot easier to manage and run the system effectively. So the nice thing about Debezium is that they've actually recently developed what they call Debezium Server. So it takes these connectors, which are written in Java, and it embeds them in a Quarkus microservice, so that rather than depending on Kafka to run, the connectors can run within a single microservice, standalone. Lindsay, I'm trying to give a talk. You growling isn't helping. No. So we're going to use Memphis here as our message broker, and we're going to look at how we connect all these pieces together, how we integrate them. This is a screen of basically one of the stations, or again, which is similar to a topic or a subject, and our display in the user interface displays our producers on one side, our consumers on the other, so we can keep track of who's sending and receiving messages, and actually displays some of the messages in the UI in case we wanted to look at them. So another key component of this, and this is really use a beautiful feature of Memphis, is we need to talk about schema on read and schema on write. So if you're used to using SQL databases, you're used to using schema on write patterns, right? So the idea is that no record is going to be inserted into the table that doesn't have, every record has to have the required fields. Now, there may be some fields that allow null values, but even then they're going to be indicated by null values versus just missing from like a dictionary or something. The database will also check the types, right? If you say this column is an integer or this column's a real number, it's going to enforce that. And so you also aren't going to have additional fields unless you do something like, you have a JSON object in a column or something. But basically, because of that, the applications that read from the database can be very sure of the data they're getting, right? They don't need to perform as much validation because they can be confident in what they're getting. On the other hand, there's a set of databases, prominently called NoSQL databases, that have become incredibly useful because they don't necessarily stick to the relational structure. So, for example, is MongoDB, which is known as a document database. And what's nice about Mongo is that you can actually store hierarchical data, right? So you may not have a fully relational case, and you don't necessarily want joins. You want to be able to go from top down into subrecords. So one of the other advantages of Mongo is that it's very, very flexible. It's often used by JavaScript developers or Python developers who can directly serialize objects into it. And so it doesn't, you don't have to like write SQL or things like that. It seems like you're just calling a library. The downside of this is that the objects may not be validated when they're written. So MongoDB does support a form of schema, but it's optional. And so what ends up happening is that there's a lot more onus on the application to do the validation. When it reads data, it needs to check, okay, I can't just go access this field. I have to make sure this field exists in the dictionary. I can't assume this field contains an integer. I have to double check that. And so it puts more onus on the application that's reading the data. And I know from my time in industry that I often got paged in the middle of the night because our pipelines crashed. We had these giant big data pipelines. At the time, we were using batch processing, and they would take, maybe 8 hours to run. We needed them to run every night. And I'd get paged and the pipeline crashed somewhere. And a lot of times, the reason the pipeline crashed is that an upstream team that we got data from either changed their schema in a way that wasn't communicated with us. So we were trying to access fields that didn't exist. Or in some cases, a lot of garbage data was actually from a customer, was pushed into a field that ended up causing problems for us. Or we even we had some custom file formats that were in like a binary format, and sometimes we'd have corruption. So are really the main cause of reliability problems for our pipelines were just problems in the upstream data that we were ingesting. And so let's say you're in a situation where your team has decided to use MongoDB and you want to build a data pipeline that listens for changes in that database and does some sort of processing. So you want to make sure that your data is clean and conforms to what you expect before it goes to your downstream pipeline, right? And so we're going to talk about a technique within Memphis called schemaverse that allows us to define a schema. And so when messages come in, if they do not match the schema, rather than being put in the station's main queue, they're going to be moved into a dead letter station, so a secondary station, where they can be retrieved later. And so this is a filtering mechanism so that bad messages or messages that don't conform don't enter your downstream system and cause problems. So it's a really great gateway at the front of your pipeline. So going back to our architecture, we're basically going to insert these to-do items into the MongoDB collection. Debezium server is going to listen for those events. And it's then going to, every time a new record is created, it's going to make a HTTP call to this REST interface, this gateway. And that's going to generate a message that goes into our to-do CDC event station. And those messages are going to have a JSON record as a payload. As we're going to see, though, when those messages, those records come out of Debezium for MongoDB, it turns out that we need to do some transformations to get a pure JSON object. And once we have that pure JSON object, then we can apply schemaverse to check those objects and direct them appropriately, either to downstream processing or to the dead letter station. This is an example of a JSON message coming out of Debezium. And so I've omitted some of the fields, right? Like there's two top level fields, the schema field and the payload field, and I'm ignoring the schema field. And there's within the payload subdocument, there's some additional fields I'm ignoring. The two key fields are before and after. So before represents the state of the record before the query was run, and after represents the state after the query was run. So if you're doing an insertion, you're going to get a record like this, where the before is null because it didn't exist, and afterwards that you have the record itself. If you update a record, you would have something in the before and something in the after. If you delete a record, you'd have something in the before and null in the after. So these two fields kind of tell you what happened. What you'll notice here, though, is that this after, the value of this after is a string. So there's a second JSON document that serializes a string. So it's a serialized JSON document within a JSON document. And so we actually need to unserialize that in order to use schemaverse, in order to check the messages. So what we want is this, right? After we've unpacked it, unserialized it, we'll see that our record has an ID field, which is what MongoDB uses to track the object ID, a creation timestamp, which MongoDB stores internally as integer Unix sort of timestamp from whatever 1970 Unix epoch, and then the description by Melk and whether it's been completed, true or false. So this is our goal. And so once we've transformed it, now we want to check that it's valid. And the way we define this, there's several ways to define appropriate records in Memphis. So Memphis has understanding protocol buffers, Avro, graph query language, and JSON. I'm focusing on the JSON case, but there's a project called JSON Schema that basically defines a sort of meta language around JSON that can be used to define what an allowed sort of object is. And JSON schema implements the schema itself in JSON. So every JSON schema object has a schema field with this $sign that points it to the version of the language that it's using. And then a type is an object. So this object has properties, And so we're saying that one of the properties is the payload property. So I'm not mentioning the schema property here because by default, JSON schema doesn't flag anything that's an extra field. You can set it to do that, but by default it doesn't. So I don't need to handle fields I don't really care about. Because I care about this payload field, it is also a type of object with the properties before and after. And then this one of is basically an or. So it's either null or it's this other thing called a to-do item that I've defined. Then we say that these two fields before and after are required. They have to be there. Now they can contain a null value in this case, but they have to be there. Note that if we didn't care about the field being there, not just requiring it there with a null value, we wouldn't make it required. So there's a slight difference in semantics there. On the top level, going back to the top level object, we are requiring this payload field exists. Okay. Further down in the JSON schema file, we can define definitions. So it makes it easier rather than repeating code over and over again. We can define the definitions once and use them. So I defined a to-do item, and the to-do item has an ID field, which is basically an object with an OID key and a string value, a description, which is a string, a creation timestamp, which is a date object with a date field and an integer, and then a due date, which a due date can either be an object of type date or it can be null. So maybe a to-do item doesn't have a due date, right? It's open-ended. Lastly, we have this completed field, which is a type Boolean. And then we're going to define the required fields as ID, description, creation timestamp, and completed. And due date is not required. So either due date can be there with a null value, or it can be missing entirely, or it can be a date object. Any of those are fine. Any questions with that so far? Okay. So now that we've kind of walked through the background, are you ready to kind of look at some code and watch this thing run? All right. So
yep,
we have available through the GitHub organization for Memphis.dev a repository called Memphis Example Solutions. And so this is all open source code that you can pull down and play with. And so right now I'm in the MongoDB Debezium example, and we have multiple files and folders here. So I just want to point you to, there's a README file that explains some of the background that we talked about in the presentation and gives instructions for starting and running the service. So I'm going to walk through this, right? So let's start here. And I've already built the images in case they might take a little while. They didn't. And then I'm going to start Memphis. So I'm using Docker Compose. And so if I do Docker Compose up/D, so D tells it to run in the background. If I start the Memphis REST gateway, that service also depends on the Memphis broker. So it'll start everything.
We're not seeing your live demo. I don't know if you're showing it yet or not.
No, I need to switch you're absolutely right. Here we go. Okay, how's that? Can you see the code?
Yes,
now?
sir.
All right, great. So we now have Memphis running. And so I can actually, I'm going to open another window here and share that. I might just share my entire desktop because that might be easier. Yeah. So I'm going to connect to the local host at port 9000, where we're running the Memphis web UI. And so the default user is root with the password Memphis, which you obviously never want in production, but for offline development is okay. And so when we log into the Memphis web UI, the first thing it does is it prompts us to create a station. So there's this really nice wizard for doing this. We're going to do to-do CDC events like that. And I'm going to leave the settings the same. And then I'm going to create a user to do CDC service. Oh, it is 8 characters long. Okay, they changed the, that's going to be a problem. Okay, so I might have to edit some code. We will see in a second. So let's do this. What is Chicago? Go try that. Why I do the passwords so much? There we go. Okay. So I've created this user, and the Memphis UI helpfully gives me code snippets for whatever programming language I might want to use. Since we have a lot of Microsoft people here, we can look at some .NET code for how you would produce messages or consume messages. Okay. We don't need that because we've already implemented it. So we're going to go to station overview, which is here. And then I'm going to create another station, which are cleaned to do CDC events. Okay, we now have our second station set up. And while we're doing that, we're going to set up our schema set up schema verse for the second station. So I'm going to copy this big block from our README file. That. And I'm going to go over to schema verse, create a schema. We'll just call it the to-do schema. And I'm going to select JSON schema. Paste this in here. I'm going to click validate. So it's great, it's valid. I'm going to create the schema and I'm going to attach it to the cleaned to-do CDC event. So now messages sent to that station will, that schema will be enforced. So let's go back here and I'm going to need to modify my Docker Compose file real quick to okay, I'm gonna make this root and Memphis so we can avoid problems. It's gonna be root and Memphis. And this is going to be root and Memphis. Okay. So after I have Memphis running, my next step is to start the rest of my services. So I'm going to start a printing consumer that's just going to print things to the screen. It's not going to show things yet, really, because we don't have any events. But if we go to the to-do CDC events, we actually see the consumer shows up here now. Okay. Should I do this? Move this over here. There we go. Okay. So now that we have that running, I'm going to start the to-do generator, which is also going to start MongoDB. Okay, so we have MongoDB running. This container here that does the database setup will actually create the collection and set the replication mode. So it enables the replication so that then Debezium can receive those events. We look at Debezium itself. I'm just going to start this up like that. So it's going to pull some images. Okay, so now we are going to go back to reload the page, and let's look at, okay, Docker logs, and look at our Debezium server containers, see what's going on. We'll just tail it. Okay, so I actually made a mistake, and that's when I changed the username and password. I didn't update the configuration file for Debezium. So Debezium server uses a configuration file like this, and we need to define the username and password. I'm going to do that. And so I'm going to do Docker build or Docker compose build. So I'm going to rebuild that image, which includes that configuration file that gets inserted. And then I'm going to restart Debezium server. All right, so now look at what's going on with Debezium server. Okay, so it's the logging here is showing that it's receiving the changes, and we now see this producer show up, and these are the messages that are being received. So you can see it's a giant JSON object with a bunch of stuff in it. Okay, so now that that's running, we want to start our transformer, right? So we want to basically take these messages from this raw station, transform them to the cleaned up version, and send them to the other stations. So we have a service that does that. Oops. You do cancel the log output. There we go. So I run the CDC transformer. And now you're going to see messages showing up here. Notice, so these are now, if I go down here, like this object all the way at the bottom here is unpacked, right? So the after looks like what we expected. But you'll notice this warning sign, this notification here. So this is messages that either have been sent to a consumer but haven't been acknowledged, or they've attempted to send to a consumer multiple times and haven't been acknowledged. And then a schema violation. So these are the messages that aren't satisfying the schema. And so you can see here that one of the fields has a value of -5,000 instead of Boolean. So the completed field should be true or false. But because this record doesn't match our schema, it doesn't get put into the main station. It gets redirected to the dead letter station. So that means that our pipeline won't be impacted, right? So now I'm going to start the printing consumer for that. And so if I show you the original printing consumer, it's this giant mess. But then if I start the cleaned one, or cleaned, you'll see now here on the bottom that these messages have been deserialized. And these are the ones that are clean. They match our schema at the end. So this is a really powerful feature to be able to basically prevent bad data from getting further down your pipeline. So kind of going back, what do we have going on, right? We have MongoDB. So we have MongoDB running. So you can see it's receiving connections over the network. We have a to-do generator. What's the name? MongoDB hyphen. And so we're outputting all these randomly generated messages or items and inserting them into the database. We have Debezium running to capture those events and forward them onto Memphis. And then in between our two Memphis stations, we have a transformer process that's basically just taking the input messages and outputting them. And it will receive an exception when the consumer being used here, or sorry, the producer being used here will receive an exception when a message doesn't match the schema. So what ends up happening is that message both gets sent to the dev letter station and the client gets an exception. In this case, this service doesn't care if it doesn't match because it ends up in the dev letter station to be handled later. So I have error handling code in here just to avoid doing that. So any questions on any of that? Anything I can show you?
Yeah, so if get back to the basics of this. So Debezium uses a Postgres database to capture the do the data capture. Is that a correct statement?
Well, in this case, I'm using MongoDB actually, but I also have an implementation for Postgres as well. So it works with either. So when you define the configuration, you have to define a sync connector and a source. So in this case, the source is the MongoDB connector, but you could easily do Postgres as well. Mm-hmm. It has plugins for MySQL, SQL Server, DB2, Oracle. Yeah, a number of different databases.
Oh, okay. All right.
Yeah.
So it's not limited to just those two.
Right. Yep.
Okay. Okay, great. Thank you.
Yep. And then we're using the HTTP sync to basically send the messages over REST to the message broker. So it's a convenient way to capture from a bunch of different types of databases into a unified streaming platform. So, all right. Well, that's what I have for you today. Thank you for attending, and I thank you for listening to my talk. You can go to our repository on GitHub, and you can download this code and run it on your own machine using Docker Compose if you want.
Okay, great. Great. Well, RJ, thank you for presenting.
Absolutely. I can stick around for a few minutes if anybody wants to ask questions or anything like that, or I also would be curious for those of you who have experience with Microsoft CDC solution, how it differs.
Yeah, actually, and by the way, thank you again for presenting to our group, and great presentation. The question I have, so I've been working with Microsoft SQL Server since the beginning of my career, which isn't as long as many people's, but but it was pretty much all I knew for a long time. And as far as relational database engines, it is as well. Obviously, being a Microsoft product and not open source, it probably has a lot more features built in over time than some other ones. So let me kind of give you an idea, right? For Microsoft CDC, I basically just pick a table, enable CDC, and it takes off, right? So it's all built in. And what I do is I can use specific functions to query the changes over time. And, it's got like an auto purge, but ultimately it's keeping track of it in kind of a, let's call it a separate table, right? That's automatically managed by SQL Server. So for me, right, if I'm using SQL and of course paying the licenses for it, I would wonder, like, and I don't know, does Postgres have something like that I can just turn on for a particular table or MySQL? And so when I look at this solution, right, coming from a SQL background, I see a lot of kind of little pieces and maybe a little bit more code and building. And I'm 100% certain that there is a use case for all of this. But knowing kind of what I just told you, why would I use, let's say, this versus the native capability? Is it a licensing thing? Is it having more control? Is it multiple sources maybe feeding in? Why would I maybe use something like this solution?
So I guess I need to ask you a question about, you mentioned how easy it is to configure and set up the CDC within Microsoft SQL Server. Where do the change data capture events end up? You make mention another table? Do they just end up in another table?
Yes. So it is another table that is kind of like attached to this table, much like a non-clustered index in a relational database, right? It's like it's really, in essence, a separate table, right? But we don't really look at it as such. And so it's similar in that respect. And then I've got specific functions and SQL code that I would use to query those changes, and then that would produce a result set, and I would use that either in my application or in a stored procedure or something like that. So it's all self-contained there, right? We don't really have a destination until we choose one based upon our application or our script.
Right. And I think that's maybe the difference here, right? So in order to use the built-in solution for SQL Server, I have to query the server, right? So my application has to periodically run a query to get that data. Here, the events are being pushed into a streaming system.
Got it. Okay.
So in some ways, that can be less, depending on the number of downstream systems that are using that data, right? You could potentially see that having to run queries every 5 minutes or 10 minutes or whatever could put some load on your server that you don't want.
Absolutely.
This is a lower load approach. And then once you put it into your streaming system, whether it's Kafka or Memphis, that handles setting it to a large number of downstream systems.
So would this solution be more geared towards event-driven architecture versus like just straight up ETL or ELT, depending on? Okay, got it. And that makes total sense to me because there is some inherent I don't want to say problems, but complexity in creating an event-driven architecture through SQL Server CDC. And so it seems like more the intent, right? Is that CDC is more for ETL or ELT, and this is more for event-driven architecture.
Yeah, I think that's a really great way of framing it. Yep. So, another thing that these event processing platforms, like whether it's Memphis or Kafka, are pretty good at, right? So they are different from traditional message queues like RabbitMQ or ActiveMQ and such, in that the traditional sort of publish subscribe type system, when messages are sent, if the consumer isn't attached at that moment, it's not going to receive the message. So that it doesn't sort of durably keep track of the messages. Now, Kafka or Memphis is going to keep they use a append-only log. So they keep all the messages up to some retention date that you set. And so if I change my downstream pipeline, like I fix something and I need to reprocess the data, I just point the streaming pipeline back. I tell it to reset its position in the log, and it basically can start wherever I tell it and reprocess all that data. So these streaming systems are a very efficient way of accessing data in the order it arrived. So.
Interesting. I would think that the CDC tables in the SQL Server are always in the order that they arrived, but I don't know. The two solutions seem very different. So.
Well, they may be in order in the table, right? But how are you? I mean, I guess other people can. If you have more knowledge, please fill this in if I'm wrong about something. But when you load that in, you're trying to query against that. You're not going to query everything in the table at once, right? So let's say that you want to go back and process 1 million messages, right? You may want to chunk that up. So you're going to have to do sort of paginated queries, right, to get each chunk. And
I think that might be the difference right there, is that CDC is more like that's just the change to the table itself, nothing more. So that's what those SQL Server CDC tables are. They're just changes to that row of data. They're not queries, they're just before after images of the change to that row in that table.
Yeah, give me the history of my data in this table, right? And that's really what CDC is. So, tell me what changed, but don't just tell me what changed. Show me the lineage of that change. Did it change 100 times? Did it change? Because we do have another technology that's really just more like, show me stuff that changed after this date, and all I care about is the end result, versus CDC, which is like, show me all of the changes to this row or this particular set of rows since a particular date.
Yeah, absolutely. And you're also making me think of something else. So I have been thinking mostly of the case of relatively small number of changes or just like tracking inserts or deletes. But if you have records that change a lot, right? Your table may go from, for every record in the original table, you could have 10 or more change data capture events in your other table.
Sure.
Right? And so now your database server, the volume of data is growing.
Yes.
And you have to manage that. And I don't know, maybe SQL Server supports this, but like Postgres out of the box is not distributed. If you need a bigger database, you need a bigger node. There are, of course, solutions out there for like Citus data that allow partitioning the data over multiple nodes, but that seems like you could run into an operational problem that way. Whereas with this, those events aren't stored in the database directly. They're on a secondary system that you would potentially scale or set up to be able to scale. Because like Kafka and Memphis are both scalable in the sense that you can add more nodes to the cluster as your data sizes increase.
Right. No, yeah, that makes sense. Same thing with SQL, right? Is that by its nature, in fact, it's very difficult to build a distributed architecture with SQL Server, right? So as your database grows, of course, you need to add more disks or more space or whatever that may be. And so it's certainly a concern when somebody's using CDC. Any type of native, I think probably CDC on any relational database that's not built to be natively distributed. And like you said, Postgres in and of itself is not distributed unless you use something like Citus, like what Microsoft uses for PostgreSQL on Cosmos DB. And as far as I know, MySQL, same thing. Like it's a relational database, and it's built to maintain properties of ACID. It's not built to be distributed.
Yeah, and I mean that's what I tell my students, right? It's the online transaction processing. It's designed to support a large number of concurrent users, each modifying a small number of records at a time. And that way you avoid locks, right? But you look at something. I had experience with using Presto when I was in industry. It does not have ACID guarantees, right? It's designed mostly for large queries that are going to process a lot of records in one go, and you have a small number of users, and they're not trying to access the same table at the same time, for the most part.
Right. Yep. Yeah. For sure.
So you
Very
can
cool.
scale SQL, but you got to give up some of those things or implement them in a different way.
Yep.
So, yeah, I haven't come up with a good way of, in my classes, a good way of describing the what we associate with a traditional SQL database, the architecture limitation there, right? Because it's not limited to SQL, the language, right? It's, again, because we have Presto and stuff, SQL can be implemented in other ways, but I don't know what to, like, I end up calling it an OLTP architecture, which I don't know if that's right or not, but
I would say it is, sure, right? But you also have your isolations, and in SQL Server now we have read committed snapshot. So read committed snapshot reduces a lot of that locking, and they've obviously, everybody's looking at optimizations to build more HTAP systems. For those of you who aren't familiar, what I'm talking about is hybrid transactional analytical, right? So data warehouse versus traditional OLTP. Most people want some type of combination of the two these days, so we can run analytics against our real-time transactional data. And that's where the challenge typically comes in now, with the engineering teams that are building these products.
Yep. Yeah, absolutely. And that's what I find really interesting about the storage space, especially in the last 10 years or so, is it's just exploding because people have identified all these different use cases. And, the solution was, well, we're going to build a different system for this or a different system for that. But now that we're starting to realize, oh, maybe these aren't incompatible after all. Cool. Well, thank you for lively discussion. And actually, your questions and Steve's questions, insights are really great, because I think I can go back to, like Steve pointed out, the difference between the CDC versus the streaming CDC aspect. Can clarify the slides and that story. So thank you. That's helpful. So.
Cool.
Yeah. All right, everybody. Thank you for your time tonight. I'm going to head out.